All right, so last two transformations we're going to look at for sine and cosine are the stretches. Okay, we did both shifts, shifting left and right, shifting up and down. Now we'll do the stretching left and right, stretching up and down. Both of these have a connection with sound. So I will demonstrate both so you can hear what it sounds like. This is also the last day of doing individual transformations. Every problem you did yesterday, every problem we're going to do today only has one transformation in it. That's it. Tomorrow we'll do some multi-step, where maybe you shift up and left. You do two things in the same problem. When we start to do multiple things, then the order becomes important. It's the same order we've done all year. Right, so we'll go over that tomorrow. Also, we're going to use graphing calculators a little tomorrow to solve equations. Basically, like a y1, y2, see where they cross kind of thing. That's all. But for today, you won't need a graphing calculator. All right. So first thing I'm going to define is what's called the amplitude of a sine or cosine function. So basically, amplitude measures the height. And the height is defined the way I show you in this picture. It's the distance from the center to the peak, which should be symmetrical from the center to the low point. Now, whenever you measure height, think about height. What kind of number does a height have to be? Yep. It has to be positive. There's no such thing as negative amplitude. Okay. So the two transformations I'm going to give you today, we're going to graph them, just like we did yesterday, but I'm also going to ask you something different. I might just give you an equation like that and say, what is the amplitude? Okay, no graphing at all. Just tell me the amplitude. So we'll practice a couple of those. So we're stretching. The operation that's always involved when you stretch, multiplication. Where the multiplication is tells you if it's horizontal or vertical stretch. Multiply in front, that's a vertical stretch, which with trig we call amplitude change. 3 out of 4 of the transformations, they give them special names when we're doing trig. This one's called an amplitude change. If I ask you for the amplitude of a function, all you have to do is take the absolute value of the number in front. The only time you take the absolute value is if I ask the question, what is the amplitude? Okay, when you graph, you don't do the absolute value. Okay? Because if there's a negative in front, we've talked about what a negative does. You don't just want to get rid of it. Because what does a negative do if you have it in front? Yep. It flips it. And that's important when you do a sketch. But it is not important when you're finding the amplitude. Flipping it keeps the amplitude, it doesn't matter. It keeps it the same. If that was your original, and then you flip it, those two graphs have exactly the same amplitude. 1 or 2, whatever it is, it's the same. Okay, so amplitude is always positive. Okay, amplitude change is going to stretch or compress a graph along the y-axis. So, anyone know what that would do to the sound? Like if you had a sound like that, and then we take that and trace over it. Take that same sound and then do something like that. I didn't stretch it left or right at all. All I did was stretch it up and down. Anybody know what would that do to the sound? Yeah?
Make it lower pitched.
Okay, so it could change the pitch. That is going to happen in one of the two we studied today. What else could it change besides the pitch? Yeah?
Frequency?
Frequency is the pitch. The frequency of the sound is the pitch. Yeah? You change the volume. That actually is a change in volume. That's a higher amplitude. Higher amplitude means louder sound. So this is a change in volume. So I can play that, but it's not a very interesting change. It just gets louder and soft. So let's try an example. No graphing at all. Here's an equation. I just want to know the amplitude. Y equals 3 cosine x. So remember how to find the amplitude. Absolute value of c. C is the number in front. And if you're wondering why did I use the letter c, it's because when we put all the transformations together, that's the third one, ABC. It's the third one you always do. All right. What's the amplitude there? Zach? 3. How about the amplitude there? Yep.
4 over 3.
4 over 3. There's other things happening too. There's a phase shift. There's a vertical shift. Neither one of those has anything to do with the amplitude. Right. You got to focus on the number that is in front. How about the amplitude of negative 2 sine x?
2.
2. Brandon, what if I did this? Still 2. That negative does not make any difference with the amplitude. All that does is flip it. Okay? So that is important when we graph, but not for that question. Okay. Any question on how to find the amplitude if they give you an equation? Pretty easy calculation. All right. So amplitude change is going to stretch and compress the graph along the y-axis. So which values, which column, the x or the y's, doesn't change? The x's. It's nice when the x's don't change because we don't have to deal with the 0, the pi over 2, 3 pi over 2. We don't have to deal with any of that. All you guys are going to have to do is arithmetic with a 1, a 0, or a negative 1 for this transformation. We're going to be changing the y values. Okay, so x's stay the same. Go to your original table that I gave you. Copy down the x's. If you do that, you get 5 points. Now, to find the new y values, take the originals from the table I gave you yesterday and multiply them by c. Notice it does not say absolute value of c. You just use the number that's in front the way it is. If there's a negative with it, use the negative. Positive, then you don't have to worry about anything. Right, so we'll see, depending on how much of this we get through, if we have like 40 minutes at the end, I might start a little bit of 6.3. Doesn't mean we're going to do extra if we finish early in 6.3 tomorrow. It would just allow me to go even slower to 6.3, and then I could maybe do a little review for the test too. Yeah. Yeah, the test will be on Friday. So if we start a little bit of 6.3 today, if we get to it, then at the end of class tomorrow, I'll do a review for the test. Because I'm not staying after tomorrow. I'm staying after today. Okay, let's try an example. Y equals 3 cosine x. All right. So Jacob, now we know 3 transformations. Phase shift, vertical shift. Now we're working on amplitude. Out of the 3 we've learned so far, which one is this, and how come?
Amplitude.
Yep. What tells you that it's amplitude?
The 3.
And can you be a little more specific about what's happening with the 3?
Change the stretch on it.
So it is a stretch, but can you explain like what operation is happening?
No.
Anyone help them out? Because I could go like this, I got a 3 in front, but now I just changed the problem to something we did yesterday. That's not normally how we write a vertical shift, but you could. That's a vertical shift. Yep.
You're stretching you're changing the amplitude on the y-axis?
Yep, I am changing the amplitude, but I still haven't heard the operation there. Like if you wanted to read that on paper, you could say 3 cosine x. But if somebody said, what do you mean 3 cosine? Like 3 what cosine? what are you doing? Yeah, multiplication. So the key here, the way you tell that's a vertical stretch, is you are multiplying in front. Multiply in front. When we multiply inside, that's going to be next. But for now, in front. Okay, so Nikera, when I do that, it's an amplitude change. Which column stays the same? The x's. And Kaya, can you tell me what my x's are? Yep. Very good. So those are my x's. Those are my x's for every single vertical stretch we do today. Okay. Now, my y values, first I want to think of the originals. Jared, what are my original y values for cosine?
1, 0, -1, 0, 1.
Yep, I put them off to the side just to remember what they are. Now, Sam, I'm going to take all those y values and do what to them? That's it, multiply by 3. 3, 0, -3, 0, 3. I mean, arithmetic doesn't get much easier than that. And that's it. There's your table. Questions on the table? All right, now we'll make our sketch. So, I'm not going to go by 1s anymore. I'm going to go by 3s. So I do need to label it. All right, this is going to be my, I didn't label this, but that's my x-axis, which, you know what, I'll put it up here. X, Y. Now, put in my other labels. 0, pi over 2, pi, 3 pi over 2, 2 pi. And we're going to go 3, 0, -3, 0, 3. 3, 0, -3, 0, back to 3. And there's your sketch. Now, that graph doesn't look like it's stretched out 3 times the size. How come? Yeah?
Because you made the units on the y-axis 3.
Yeah, and I'm always going to do that. So like if you wanted me to graph 30 cosine x, I just go like this. I'm not going to try to draw it 30 times as big. I don't have that big of paper. So I'm going to change my scale. That's why every graph I do today for cosine is going to look the same. Every graph I do for sine will pretty much look the same when you're doing a stretch. The way I do it. Okay. Any questions on that? All right, so I told you I could play what that sounds like. It's not super interesting, but in terms of sound, if you look at what happens, that's a vertical compression. And if I play it, give it a second. You hear that? Now if I do a vertical stretch, oh wait, it does that one smarter. Works fine if I go away from it. You can see it's a lot louder. Right. And that's basically what happens with a vertical stretch in terms of sound, louder and softer. Now, there's other kinds of things in science that we model with waves, like electromagnetic waves. Those are things like visible light, ultraviolet, microwaves, radio waves, X-rays. Those are waves too, but they're totally different. You don't hear any of those. You don't hear microwaves. You don't really hear microwaves. You don't hear radio waves. You don't hear X-rays. You see visible. Okay, your eyes can see a small portion of electromagnetic. They can see visible light, and that's it. If our eyes were more sensitive, then you would be able to see X-rays. You would be able to see microwaves in the air, right? But our eyes aren't. Our eyes aren't set to those frequencies, so we can't see them, right? Sound, same thing. We have certain frequencies we can hear. Right? So what would happen with an amplitude change? What do you think would happen with an X-ray? If you change the amplitude of the X-ray? You don't get a louder X-ray. What would you get? Yeah. A more what? Well, and I don't know. I guess it depends on how you develop. I don't know much about developing an X-ray, but I do know, like, if you showed me two X-ray signals and one was like that, and then you compare it to an X-ray signal that, I'd have to go back to my desk, but that was compressed. The difference between the two would be,
I feel like the bigger the amplitude, the further it can like penetrate into something.
yeah, it's intensity. Intensity is just how you perceive it. If it's a sound, you perceive intensity as louder. If it's an X-ray, you would perceive intensity as something that is a stronger X-ray, meaning it could go through more material. Maybe it could go through deeper, all right? Same with a radio wave. Stronger radio signal means it could travel further. You could pick it up further away from the radio station. So amplitude change always has to do with intensity. Yeah.
All waves like that usually move slower though, right?
What's that?
No move, or waves that are taller like that move slower though.
Are you talking about for sound or like electromagnetic?
Like radar.
So yeah, that would fall under, I think that would fall under electromagnetic. They all travel at the same speed, the speed of light. Okay. Whether you have an X-ray or visible light or anything, they all travel at 186,000 miles per second. Very fast. You can't really easily change the speed of an electromagnetic wave. Yeah. Pretty constant. It's like turning on a flashlight, the amount of time it takes from when it turns on to when the light hits the back of the wall. It seems like it's instant, but if you could have like a laser and point it at the moon, you could actually measure the time it takes for the laser to reach the moon. You could have, I think they have mirrors.
They do.
And it can bounce back. But yeah, the speed is pretty much always the same. For sound, the speed is not the same. Speed of sound depends on lots of things. Depends on the medium it's traveling through. Air is very slow. So in this room, you're so close to me, there's not much of a delay from when I talk to when you hear it. But if you were outside and somebody was like 3,000 feet away from you and they had an air horn, there'd be a real delay from when they press it to when you hear it. There's less of a delay through solid matter. So like if I have a metal rod, like 3,000 feet long, you have your ear on one end of it, and I take a hammer and I hit the other end, you'd actually hear it twice. You'd hear it through the rod first, because the sound travels very fast. And then if you lift your head quick enough, you'd hear it again through the air. You'd hear it twice. So the speed of sound, it also depends on temperature. Cold temperature versus warmer temperature. Sound travels faster and slower. Yeah.
So is the speed of sound just the fastest sound will go?
Is what that?
Or
Well, sound can travel at different speeds.
hold on, I
I think if the air temperature is warmer, it travels faster. If it's colder, it travels slower. Because think about it. Sound has to vibrate air. If things are cold, they vibrate slower. It's like you. If it's cold, you might move a little slower. If it's hot, think of boiling water. Molecules are moving real fast. It's easier to vibrate now.
But like when a jet breaks the sound barrier, isn't that like 762 miles an hour, like specific speed?
So when we break the sound barrier, I think it would have to do with the temperature of the air around it.
Because I thought that was like a set speed was the
Yeah.
Because I think it's like 700 something miles an hour.
Yeah, it is around 700 miles an hour. Maybe it's 700 miles an hour at 50 degrees temperature. I mean, it doesn't change
what I mean,
much.
is that's like a specific.
Yeah,
Okay.
might be specific. I mean, maybe if it was 40 degrees, it might be 750.03 or something. I mean, it doesn't change a lot, but it would change a little. Not a lot. All right, let's look at this one.
It takes a little work to get the end out to get to the speed,
So- Another vertical stretch. But what do you guys think is going to happen on this one compared to the last one? It's going to shrink. right? This would be a decrease in intensity. Sound means it's going to be quieter. Electromagnetic, it's going to be less intense, whatever that means. If it was visible light, it would mean it's a dimmer light. Okay? So, x's are going to stay the same. 0, pi over 2, pi, 3 pi over 2, 2 pi. Caleb, what are my original y values for sine?
Oh. Zero, 1, 0, -1, 0.
Yep. 0, 1, 0, -1, 0. And Emily, what am I going to do to all those values? Multiplying by, multiplying by 1/2. So 0, half, 0, -1/2, 0. But you can do 0.5. That's fine too. Okay, so let's graph it. Again, this graph is going to look exactly the same as all my others because I'm going to scale my graph on the y-axis by 1/2. 0, pi over 2, pi, 3 pi over 2, 2 pi. Right, and we're at 0, half, 0, -1/2, back to 0. And there's your sketch. Questions on that? All right, let's look at this one. Now, what's happening there? Brandon, what's going to happen there?
Yeah, 2, 1.
The amplitude is still 1, but what's the negative going to do? So you mean if I were to graph that or I were to graph that, they would look exactly the same?
It would flip.
It would flip. Okay, that negative is going to cause it to flip. So there is no change in the amplitude, that is true, but it will flip. So 0, pi over 2, pi, 3 pi over 2, 2 pi. All right, so Eric, if I flip that, can you tell me what my y values would be for cosine?
It would be same cosine.
Well, it's going to flip, right? So if it's going to flip, something's going to change. And it's not the x's that change because I already wrote those down.
Oh, wait. So -1, 0, 1, 0, -1.
Yep. So 0, 1, -1. I'll label that. 0, pi over 2, pi, 3 pi over 2, 2 pi. And we're at -1, 0, 1, 0, -1. Now remember, that's supposed to look like a wave. Don't make it like a V upside down. Try to make it look something like this. And it would continue like that.
Looks like the sound difference. Where is it?
I don't know of any real sound difference or application to sound. I don't think there really is one. All right, so last thing we're going to look at is what's called a period change. Now, very first thing I mentioned on Monday was the period of sine and cosine. Does anybody remember what's the normal period, the length of one cycle, if you don't mess with it at all? Yeah.
From 0 to pi, or 180 degrees.
You don't know this yet, but when we study tangent and cotangent, the period is 180. But for sine and cosine, it's 2 pi. Yep, it's 360. 2 pi means that's the width you would have to set your calculator window from x min to x max in order to see a full cycle. Now what we're going to do is we're going to stretch or compress it. Okay, we're going to change the cycle. And in terms of sound, this one is the most I think, interesting one to hear. Okay. So what operation am I going to use if I'm going to do a stretch? Multiplication. And it's going to be inside, because this is going to be a horizontal stretch. So a period change is just a fancy word for horizontal stretch. It's the same thing. Now the reason I use the letter B, well, you tell me. Why do you think I use B? Yeah.
Because like that comes before the you do C.
That has to do with the precedence when you combine multi-transformations in the same problem. So it has the form y equals sine bx. Now, what do we know in general anytime we do horizontal transformations? What do we always want to remember? Yeah?
That affects the X.
It will affect the x. Something else about horizontal transformations. Else remember? What happens, what do you always want to remember when you do horizontal transformations? And this happens in every function we've studied all year. Yeah? Kind of. Yeah.
Positive is left, negative is right.
Okay, that's for a phase shift. So summarize that idea in general. With horizontal transformations, you always what?
Flip the signs kind of, or
You do the opposite, right? Because you're not going to have a plus or a minus here necessarily. So if I put a big number in front of x, like 5,
it'll compress it.
it'll compress it, right? Bigger numbers make it smaller. Smaller numbers make it bigger. What's a small number? 1/3. Right? So horizontal transformations are always the opposite of what you would expect. Now, we could do an example where b is negative, and that would be a horizontal reflection. But we're not. Okay, we're going to stick to examples where b is always a positive number. So, a period change is a stretch along the x-axis. I'll come right back to that, but just to show you guys what this would look like. There's a graph. Take this, copy of it. This is what a stretch or compression would look like along the x-axis. So there was no change in the height. The height of the wave is exactly the same. You just compress the wave into a shorter space. And that would change the pitch. High pitch, low pitch. So, two things we want to remember. I just said these. If you put in a big number, it makes it smaller. A small number makes it bigger. Where's the division between a small and a big number? 1. Bigger than 1, it will compress. Less than 1, it will stretch. All right, so the standard tone that I've been using as an example for you guys is 1000 hertz. Okay. Remember, hertz means cycles per second. So if I play that, okay, you can hear it. It's a frequency of 1000 hertz. As I start to compress it, you can, if you look closely, you can see it actually stretching and compressing. So I've compressed it. And now this is a frequency of 3000 hertz. So it's higher pitch, but it's nowhere near what we can really hear.
Go higher.
I'll go a little higher.
Wow. Go to like the observable.
So this is 6000 hertz. Now I played 3000, I'm playing 6000. You can't really say it's like twice the pitch. That doesn't really make sense. Because pitch, if you look at frequencies and you look at musical notes, you can learn more about how notes correspond to frequencies. But for our purposes, this is double the frequency. Okay? Does that mean it's twice as high pitch? I don't know. But it's double the frequency.
Oh my.
So it's again a little higher.
A lot.
No.
I'll see what I can hear.
So we'll go. So we doubled it. We'll go to 12,000. So I'm gonna play it. If you don't want to hear it, you might just want to block your ears, or you can step outside if you have really sensitive hearing. All right. So this is 12,000. So you're hearing a couple things. First of all, my speaker's kind of freaking out a little. Like I'm almost hearing a buzz.
That's just the electricity.
So that really shouldn't happen, but it's just the high pitch you're hearing. So if we go up to 17,000. Now, that buzzing, you really shouldn't be hearing the buzzing part.
Or no.
But that's really high pitched. Anyone that can't hear the high pitch part of that? No? You hear it?
It's correcting my nodding my head.
Now, if I play it up here, I'm hearing like a clicking. That's not the sound. And that sound you hear, that's not the sound. So you can't hear it. Now, if I bring it down a little bit, that's this crap. It says 18,400. Now,
Does it have tweeters in it?
yeah, those are tweeters. Now, you might think, well, how do you even really know that frequency is playing? Well, I can show you that it is playing. Because what I can do is turn on the oscilloscope, and you'll see a spike at 18,000 when I turn it on. I'm going to turn it down a little so I don't get as much of that crackling. So I'm just going to turn it down a little bit. Kira.
The dog is tweaking right now.
All right, so when I play that, okay, does anybody hear it? You hear it? Anybody not hear it? You don't hear it? Tell people know. All right, let's look at the oscilloscope. So what I'm going to do now is I'm going to put it on frequency. This is a graph of every frequency that's in the room. Okay, when I turn it on, you see a spike right there. You see another spike. I'm not really sure what that is.
That's probably just like the speakers blowing up a little bit.
But there's a spike right there. Now, if I take the frequency and I start to move it, you will see that spike.
If you're making noise.
You'll see that spike move. See it moving to the left? Because I'm lowering the frequency.
This is not
I love the shape of that graph.
Yeah, that's trippy.
And
Like
if
3D glass.
see how it says right there,
I can
15,366?
hear this and it's really annoying.
If I play that right here, it should say 15.366. Because that's the frequency.
It doesn't even sound like it. It's just pressure in my head.
Yes.
I
Now, we can also go kind of the opposite way. Play a lower pitched sound.
You should play some of those songs from that draws like the.
Oh, that's a number.
It's a little bit lower pitch. Now, what I need to do is eventually what's going to happen is the speaker is going to change which sound's playing it. The front speakers handle down to about where I played. Now it's going to start playing out of the sub that's above you. So you got that? This is about as low frequency as I can play.
Jesus.
Turn on the microphones if you.
Yeah, you could probably see it on the oscilloscope.
People downstairs mostly feel raptured.
Now, as I start to, if I increase the frequency, there's different objects in this room that resonate at different frequencies. Resonate basically means you play a certain sound, and that thing starts vibrating at that frequency. So if I start increasing the frequency, all of a sudden you'll hear different things vibrating. You'll hear it. I'm going to slowly increase it.
Like everything.
Nothing yet.
Like eardrums.
It feels like
Oh.
That's probably the lights.
Yeah, it's like the opera singers blows up like some Hallmark or something. That's exactly what it is.
See, now I feel it at the desk a lot.
Yeah.
I wasn't feeling it at the desk before.
We have that.
Oh yeah, some.
Oh, now I feel it.
Now I'm losing the vibration.
It's
Something else
like a
I
nice shoe.
Next door. Now nothing's resonating. I think it's too high. But
Just like get a wine glass and then just play it at the exact frequency.
yeah, you could if you had a wine glass. The way you do it is you just like flick it with your finger, get that ping. This oscilloscope would register the frequency of the ping, and then if you play that frequency very loud, that would cause the glass to vibrate. It would have to be very loud, and only that piece of glass. You could have two wine glasses, and one might vibrate at a frequency of like 2,000, and one might be 2,010. So each wine glass could be a little different. Right? Now in this room, the glass in this room doesn't really vibrate because if you were to flick the window, it's just like a thunk because it's held in on each edge. Okay? In order for a glass to vibrate, it has to be freestanding like a glass. And then it can vibrate. Same idea if you took a wine glass and you put your hands around it and held it. It's not going to vibrate. Right? It has to be able to vibrate freely. All right, so just like we did with amplitude change, I'm going to ask you guys a question. I'm going to give you an equation, and all I'm going to do, you're not going to have to graph it right away. Just going to ask you, what is the period? Okay, what is the period? So that is the formula to find the period of sine or cosine. You take 2 pi and you divide by b, which is the number in front of x. 2 pi divided by b. And what that will tell you is, where does the cycle end? It's going to start at 0. It's going to end at the length of the cycle. Where does it end? So, let's try this. Find the period of sine 2x. Okay, so what's going to be my fraction that I set up? Yep.
2 pi divided by 2.
2 pi divided by 2. Is that a smaller or larger than the original cycle? Smaller. The original cycle was 2 pi. That's 1 pi. That means you have compressed this graph by a factor of 2. I guess another way to say it is you stretched it by 1/2. Could say that. Stretching by 1/2 really means you compressed. Right. How about this one? What's going to be my fraction that I set up to find the period? How about Chris? Well, what's my numerator going to be? Anyone help him out? What's the numerator always in that formula? Yeah? 2 pi. 2 pi. 2 pi divided by what goes in the bottom? Yeah?
1/3.
1/3. What do you get if you divide 2 by 1/3?
0.6.
2 divided by 1/3. Six. 2 divided by 1/3 is 6. So what's the period of this one?
6 pi.
6 pi. Is that bigger or smaller than the original? Bigger, 3 times bigger. Right? So when you put a 1/3 in front, it actually stretched it 3 times as much. Small numbers make it bigger, longer cycle. Right? How about this one? How about Caleb? What would be my fraction to find the period here?
The 2 pi divided by pi.
2 pi divided by pi. So the cycle here is 2. Cycle of two radians. And how about this one? What would be the period of 2 sine 3x plus 3? Chris? I like the 2 pi, but it would be 2 pi over 3. Okay, those other numbers are just there because they're other things. That's an amplitude change. Has nothing to do with this question. That plus 2 at the end is a vertical shift. Has nothing to do with this question. So, how do we find the 5 points? And then we'll finish up with a graph. Which column is not affected by period change?
Y.
The Y column. We are stretching left and right. You're not doing anything up and down. Unfortunately, when the Y's stay the same, you've got to deal with all the X's. So now you've got to deal with all the fractions with pi. There's a couple different ways I can show you how to do the X values. I'm only going to show you one. And the way I'm going to show you is that. Remember, we're doing the opposite. Because we would be multiplying the X by a number. Well, it's horizontal, so we do the opposite. We're going to divide all the X's by the number in front. Take all the original X values and divide them by B, which is the number in front. That's it. All right, so we'll try a few examples, and then that'll be it. Okay. Sine 1/2 x. Okay, step 1. You have to identify what transformation that is. What operation am I doing with the number in this problem? What arithmetic operation? Well, think of it like this. It's just 0.5x.
Multiplication.
That's multiplication. Where is the multiplication?
Inside.
Inside. Okay? You have 4 options when you look at a transformation. Multiplication inside, multiplication outside. Addition inside, addition outside. Depending on which one of the 4 it is, that tells you what kind of transformation. And you could have subtraction too. Same thing, just shifts the other way. All right, so this is multiplication inside, which means it's a period change. Eric, what column stays the same?
Y.
Y. 0, 1, 0, -1, 0. Now, my original x's, 0, pi over 2, pi over 2, 2 pi. And the directions say to divide those by b. So we are going to divide all of those by what? I'm going to divide them all by 1/2. Now, that's kind of confusing to me. I don't really want to have to divide by 1/2. Dividing by 1/2 is the same as what? Yep. Exactly. That's how I'm going to think of it. I'm going to multiply all of these by 2. So 0 times 2 gives me 0. Pi over 2 times 2. Pi. Pi times 2.
2
3 pi over 2 times 2?
pi.
2 pi times 2.
4 pi.
There's your values. 0, 1 pi, 2 pi, 3 pi, 4 pi. And that's it. Now, let's go like this. Pi, 2 pi, 3 pi, 4 pi. And make your sketch. So, x-intercept goes right through the origin. That's the high point in my graph. Another x-intercept. That's the low point. And we're finishing back where we started. Now that graph looks exactly the same as every sine function I've drawn because I changed my scale. But really, it has been stretched. The original would look something like this. That's the original. The new one has been stretched out twice as much. Question on one. Right, let's look at this one. Cosine 2x. And then there's one more, and that's it. Brandon, what operation is happening here with the number? Multiplication. Where is it? So that's, how do we describe where, though?
Oh.
Inside the function or outside? Inside. Okay. You would multiply the x by 2 first and then take the cosine. Right? So the 2 comes first. It's inside cosine. All right, Jacob, which values stay the same?
Wise.
Yep. And Kara, my y's for cosine? There.
1, 0, 0.
Now, take all my original x values. And what am I going to do to all my x values this time? Divide by 2, which is the same as what?
Multiplying by a half.
Yeah, I like to think of it as multiplying by a half. For me, it's just easier to think about. Just to put times a half on all of them. Right. So the first one, what's 0 times a half?
0.
0. Pi over 2 times a half?
I have 4.
Pi over 4. Pi times a half?
Pi over 2.
It's pi over 2. What about 3 pi over 2 times a half?
3 pi over
3 pi over 4. And 2 pi times a half?
2 pi over 2.
2 pi over 2, which is how much?
1 pi. 1 pi.
1 pi. Now, if you look at that, you might see there's no pattern there. There is a pattern if you write everything with a denominator of 4. 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Right. If I had to keep going, it would be 5 pi over 4, 6 pi over 4, 7 pi over 4. There's your pattern. Okay. Is there any question on how you would do the sketch for that? It would look exactly the same as every cosine function we've done today. You just label your x-axis with the numbers in the x column. And the y-axis, technically, you don't have to label because you're going to go by ones. At least I would go by ones. Okay, let's finish up with this one. Again, same type of problem. It's multiplication inside the function. So we just did cosine. Copy your y's. 1, 0, -1, 0, 1. Sam, what are my original x values? I know I keep writing them, but just make sure I remember them.
0.
Yep.
Pi over 2. Pi. 3 pi over 2. 2 pi.
2 pi. Now, what am I going to do to all my x values here? Just say it the way the directions said it in the notes. And then we'll see if we can make it simpler.
Multiply by pi over 3.
So take all original x values and divide them by b.
Divide them by pi over 3.
Going to divide them all by pi over 3. Now that's kind of confusing. What's another way to say divide by pi over 3? Okay. Multiply by
3 pi?
no. So like if I was going to do this, 2/3 divided by 4/5, how would you do that? Yep. Yes. So do that exact same idea right here. Instead of dividing 0 by pi over 3, what are we going to do? Yeah? Yes. You're going to multiply everything by 3 over pi. Now, at first you might think that's going to come out pretty awful. But it's not. Watch what happens. What's 0 times 3 over pi? 0. What happens when you multiply pi over 2 times 3 over pi? Pi's cancel out, and what are you left with? 3 over 2. What's pi times 3 over pi? 3 pi over pi, which is just 3. Now, hopefully now you can start to see the pattern. What's the next x naught value going to be?
4.5.
4.5. And the next one?
5.
No.
Oh, no.
What are you going up by? 0? Would you go, how do you get from 0 to 1.5? Add 1.5. So add 1.5. What would the next one be after 6? 7.5. And then 9, 10.5, 12, 13. So you could just keep adding 1.5 each time.
This answer's in radians.
Yep, those are in radians. Yep. Your x column is always in radians. So now if you wanted, you could leave your labels off everything and just graph it like this. So let's say 0, 1, 1.5 would be about right there. 1, 2, 1, 2, 3. -1 could be there, assuming this is my x. This is this is my y. This is my x. I'm gonna run out of space, I think. 4.5, 0. 1, 2, 3, 4.5, 0. I'm gonna need one more, like that. 6, 1. 1, 2, 3, 4, 5, 6, 1. There you go. Here's your sketch. So this is the first time we ever had an x-axis where we didn't have pi. That's the way it worked out. All right. So homework tonight. Going to be 8 questions in a packet. So it'll be those 8 questions. Don't forget, I am after school if you need extra help. And make sure you show the table. Okay, make sure you show the table.